Good morning, dear students. This will be our last lecture of chapter number 4. In this lecture, we are going to solve these problems 12 to 15. Okay, so we start with problem number 12. So, problem number 12 is I have written over here. What is problem number 12? Show that the point x is equal to infinity is a regular singular point of legendary equation, and legendary differential equation is written over here, which is 1 minus x square y double dash minus 2x y dash plus l into l plus y is equal to 0. Now this legendary equation, we have to find out singularity at x is equal to infinity. So in problem number 12, okay, given equation we can write as, by dividing this equation by 1 minus x square, we get y double dash minus 2x divided by 1 minus x square y dash plus l into l plus 1 y is equal to 0 divided by 1 minus x square. Okay, so here if you divide on the right hand side 0 to 1 minus x square, we will get 0. Now compare this equation with standard equation, which is y double dash plus p of x y dash plus q of x y is equal to 0. We get p of x as minus 2x divided by 1 minus x square, and q of x as l into l plus 1 divided by 1 minus x square. Okay, so this is p of x and this is q of x. Now we know the procedure to find out singularity at infinity. Okay, what is that procedure? We have to put z as 1 upon x in these equations. Okay, so what we will get? We get p of 1 upon z is equal to, so here we have put x is equal to 1 upon z, so minus 2 divided by z. Okay, so here we have put value of x as 1 upon z, and 1 minus x square, which is 1 upon z square. Now this is equal to, we have to simplify this. Okay, so this is equal to minus 2 upon z, and this is z square minus 1 divided by z square. Okay, so this z will cancel with z square, and we get minus 2z divided by z square minus 1. This z will go to numerator, so 2z divided by z square minus 1. So that is p of 1 upon z, and q of 1 upon z is, so here we have to put x as 1 upon z, so this is l into l plus 1 divided by 1 minus, sorry, 1 minus x square, which is 1 upon z square. So this is equal to l into l plus 1 divided by z square minus 1. If you do cross multiplication, z square minus 1 divided by z square, which will go to numerator, so z square. Okay, now here we can find out p dash of 1 upon z and q dash of 1 upon z. So first of all, p dash of 1 upon z, which is 2z cube minus z square P of 1 upon Z upon Z raised to 4. Okay, and Q dash of 1 upon Z, which is Q of 1 upon Z divided by Z raised to 4. Okay, so we can find out P dash and Q dash here. So first of all, P dash. Now this is equal to 2Z cube minus Z square into P of 1 upon Z. And P of 1 upon Z is what? Minus 2Z upon Z square minus 1 divided by Z raised to 4. Okay, and here Q dash of 1 upon Z, Q of 1 upon Z is L into L plus 1 Z square divided by Z square minus 1 Z raised to 4. Okay, now P dash of 1 upon Z is equal to 2Z cube minus 2Z cube. This minus minus we will get plus, and 2Z cube, okay, divided by Z square minus 1 upon Z raised to 4. Okay, so we can simplify this further. So that will become by cross multiplication in the numerator. Okay, first of all we will solve this numerator. What it will become? So 2Z raised to 5, okay, minus 2Z cube plus 2Z cube divided by Z square minus 1. Okay, now this 2Z raised to 5 minus 2Z cube and plus 2Z cube, this two term will cancel each other, and we end up with 2Z cube divided by Z square minus 1. Okay, and we can write this as 2Z raised to 5 divided by Z raised to 4 into Z square minus 1. Okay, now this Z raised to 5 and Z raised to 4, we will get only 2Z upon Z square minus 1. So that is P dash of 1 upon Z, and Q dash of 1 upon Z is this Z square divided by Z raised to 4. So here in the denominator we will get only Z square. Okay, now we can check singularity at Z is equal to 0. Okay, so at Z is equal to 0, which is nothing but x is equal to infinity. Here we have to check singularity. So limit as Z tends to 0, P dash of 1 upon Z, and limit as Z tends to 0, Q dash of 1 upon Z. Now this limit as Z tends to 0, P dash of 1 upon Z. So P dash of 1 upon Z is 2Z upon Z square minus 1 is equal to, if we put value of Z is equal to 0, so 2 into 0, which is 0, so in the numerator we have 0, and in the denominator Z square, which is 0 minus 1. So 0 divided by minus 1, so this is 0, and which is finite. Okay, now Q dash of 1 upon Z. For Q dash of 1 upon Z, what we will have? Limit as Z tends to 0, Q dash of 1 upon Z is this. So L into L plus 1 divided by Z square into Z square minus 1 is equal to. See, if you put value of Z is equal to 0, L into L plus 1 is a constant. Here 0 minus 1, which is minus 1, minus 1 multiplied by 0. So L into L plus 1 divided by 0, and that is nothing but infinite. Okay, thus we can say Z is equal to 0 is singular point. Okay, now to find type of singularity. Okay, we know that how we will find out the type of singularity. For finding type of singularity, we have to take limit as z tends to 0. Okay, to find out type of singularity, where we will find out, I will rub this out. Okay, so we solved this problem number 12, that's why I will rub this out. We have to take limit as z tends to 0 z into p dash of 1 upon z, and limit as z tends to 0, I will continue from here to here, limit as z tends to 0, okay, of z square into q dash 1 upon z. So this is equal to, first of all, this limit as z tends to 0 z p dash 1 upon z. So z multiply by p dash 1 upon z. Okay. So p dash 1 upon z is this. If you multiply this with z, so that will become 2z square divided by z square minus 1. If you put value of z is equal to 0 here, so 2 into 0, in the numerator we have 0 divided by minus 1. So 0 divided by minus 1, which is 0, and that is nothing but finite. Similarly, z square q dash. So q dash is this. If you multiply this with z square, so that z square will cancel with this z square, and we end up with L into L plus 1. So limit as z tends to 0, L into L plus 1 divided by z square minus 1, and this is equal to, if you put value of z is equal to 0, so this is 0 minus 1, which is minus 1, and we end up with minus L into L plus 1, which is again finite. Why? Because this L is a constant term. Since z into p dash and z square into q dash both remains finite, we can say x is equal to infinity or z is equal to 0 is a regular singular point. Okay, then z is equal to 0 or x is equal to infinity is a regular singular point of this differential equation. Okay, now we are solving problem number 13. Okay, so problem number 13 is the hypergeometric equation is for hypergeometric equation, which is written over here, show that x is equal to infinity is regular singular point. Okay, so hypergeometric equation is written over here, x into x minus 1 y double dash plus, I think I will rub this out that you will get clear cut idea. Okay, now problem number 13. So here we have given this differential equation. So we know that we have to convert this differential equation in which coefficient of y double dash must be 1. So we have to divide this equation by x into x minus 1. So that equation becomes y double dash plus 1 plus a plus b into x minus c and divided by x into x minus 1 multiply by y dash minus alpha divided by x into x minus 1 y is equal to 0. Okay, now we have to compare this equation with standard equation. What is that standard equation? Y double dash plus p of x y dash plus q of x y is equal to 0. We get p of x as 1 plus a plus b, okay, multiply by x minus c divided by x into x minus 1, and q of x as minus alpha divided by x into x minus 1. Okay, now to check singularity at x is equal to infinity, we have to put z as 1 upon x in this equation. Okay, if we put value of z as 1 upon x in this equation, what we will get? See, p of 1 upon z is equal to, what is that? 1 plus a plus b, okay, multiply by x. But x is what? 1 upon z minus c divided by jx, which is 1 upon z, and 1 upon z minus 1. So that is x into x minus 1. And we can simplify this as, if we do cross multiplication, okay, so 1 plus a plus b, okay, minus c into z divided by z into, okay, this cross multiplication, z into, first of all, 1 upon z, okay, multiply by this 1 minus z, okay, upon z, cross multiplication of this. So this z will cancel with this z, okay. Now 1 minus z, and this z go to numerator, multiply by over here. So this is p of 1 upon z. Similarly, q of 1 upon z can be written as, now see, q of 1 upon z is minus alpha divided by x, which is 1 upon z, multiply by 1 upon z minus 1. Now this is equal to, so again this 1 upon z goes to numerator, so here we will get that z. And if we do cross multiplication of this 1 upon z minus 1, so this is 1 minus z, okay, upon z, so that z go to numerator, so minus alpha z square into minus 1 minus z, so that is q of z. Now using formulas of p dash of 1 upon z, which is 2z cube minus z square p of 1 upon z divided by z raised to 4, and q dash 1 upon z as q of 1 upon z divided by z raised to 4, we get, what we will get? See, first of all, p dash of 1 upon z as 2z cube minus z square multiply by p of 1 upon z, which is this. So if you multiply this by z square, we get 1 plus a plus b, okay, minus c into z multiply by z cube. Okay, if you multiply this by z square, here we will get z cube divided by z raised to 4. Now this is equal to 2z cube minus z cube. Okay, so 2z cube minus z cube, so that becomes z cube, okay, minus this a plus b remain as it is, minus c into z, okay, multiply by z cube. Only this z cube factor will reduce this okay, divided by z raised to 4. So that is p dash. Similarly, q dash of 1 upon z is equal to, now q dash is q of 1 upon z, which is this. So minus alpha z square 1 minus z, and divided by z raised to 4. So this z square and this z raised to 4 will reduce to minus alpha, okay, 1 minus z upon z square. Okay, this will reduce power of z raised to 4 to 2. So we have now p dash and q dash. Now at z is equal to 0, which means x is equal to infinity, we have to take these two limits. By taking these two limits, we can find out whether z is equal to 0 is singular point or not. So limit as z tends to 0, p dash of 1 upon z, and limit as z tends to 0, q dash of 1 upon z. So first of all, this limit, and after this limit. So this limit becomes limit as z tends to 0, p dash, which is z cube minus a plus b plus cz multiplied by z cube divided by z raised to 4 is equal to. Now if you put value of z is equal to 0 in this equation, so 0 minus z cube means this term will become also 0. So all numerator term becomes 0. Okay, so 0 divided by z raised to 4, which is 0, and this is 0 upon 0, which is infinity, indeterminate state. And for z is equal to 0, q dash, so this is limit as z tends to 0, q dash is minus alpha 1 minus z into z square. Okay, now this limit, what is the value of that limit? See, at z is equal to 0, here what we will get, this is equal to, here we have, here we have, what we will have when we put value of z is equal to 0. So alpha 1 minus 0, which is 1, so alpha upon 0, which is again infinite. So therefore, since p dash and q dash becomes infinite, we can say z is equal to 0 or x is equal to infinity is singular point. Now to find out type of singularity, we know the procedure to find out type of singularity. So I will rub this out. Problem number 13, we have to show that is regular singular point. Okay, so remember this, regular singular point. So I will continue this problem over here. Now we have to take limit as z tends to 0, z into p dash 1 upon z, and limit as z tends to 0, z square into q dash 1 upon z. Okay, now first of all this limit, so z multiply by 1 upon, oh sorry, p dash of 1 upon z. So if you multiply this equation to z, so here in the denominator we will get z cube. Okay, so what is that equation? Z cube minus 1 plus z cube minus a plus b, a plus b minus cz, okay, into z cube divided by z cube. Now this is equal to, so here this z cube will cancel with this z cube and we end up with here 1. Okay, and again this z cube will cancel with this z cube. So our equation is 1 minus a plus b minus cz. If you put value of limit as z tends to 0 in this equation, so this cz term becomes 0 and we get 1 minus a plus b, and this term is finite. Similarly, z square q dash of 1 upon z, if you multiply this term by z square, so this z square will get cancelled and we get limit as z tends to 0, okay, minus alpha divided by 1 minus z. Now if you put value of z is equal to 0 in this equation, so here we get minus alpha 1 minus 0. So minus alpha 1 minus 0 is 1. So here we get minus alpha, which is again finite. Since both these limit remains finite, we can say z is equal to 0, which is x is equal to infinity, is a regular singular point of given differential equation. Okay, so in this way problem number 13 is finished. Now we are moving to problem number 14. So problem number 14 is explain whether point at infinity is an ordinary point or singular point of Hermite differential equation, which is y double dash minus 2x y dash plus 2 lambda y is equal to 0. Find nature of singularity. So given differential equation is this: y double dash, okay, minus 2x y dash plus 2 lambda y, okay, is equal to 0. So again compare with standard equation, which is y double dash p of x y dash plus q of x y is equal to 0. We get p of x and q of x as, see, p of x is coefficient of y dash, which is minus 2x, okay, and q of x is coefficient of y, which is 2 lambda. So again put z is equal to 1 upon x, because we have to check singularity at infinity. So if you put z is equal to 1 upon x, what we will get? So p of 1 upon z as, okay, so p of 1 upon z, here if you put z is equal to 1 upon x, so x is equal to 1 upon z, so minus 2 upon z, okay, and q of 1 upon z as 2 lambda. Now p dash, p dash is what? 2z cube minus z square p of 1 upon z, z raised to 4, and q dash, which is q of 1 upon z and z raised to 4 we get. First of all, p dash, okay, so p dash is 2z cube minus z square multiplied by this, so that is minus z square into minus 2 upon z divided by z raised to 4 is equal to, so this minus minus will become plus and this z square, so 2z cube plus 2z, okay, divided by z raised to 4. So if you take z common from numerator, so here you will have 2z square plus 2 minus divided by z cube, okay, so that is p dash. Similarly, q dash, and q dash of 1 upon z is equal to, now q of 1 upon z, which is 2 lambda, and divided by z raised to 4. So at z is equal to 0, we are checking singularity at z is equal to 0, which is x is equal to infinity. Limit of p dash 1 upon z is limit as z tends to 0, p dash is what? 2 z square plus 2 divided by z cube is equal to. Now if you put value of z is equal to 0, so 2 into z square, which is 0. So 2 divided by 0, which is infinity. And limit of q dash is what here? 2 lambda divided by z raised to 4. If you put value of z is equal to 0, so 2 lambda divided by 0, which is again infinity. So therefore z is equal to 0 or x is equal to infinity is singular point. Now to find out type of singularity, again we have to find out this. So limit as z tends to 0 to find out type of singularity. I will rub this out. Okay. So to find out type of singularity, we have to take limit as z tends to 0, z into p dash 1 upon z, and limit as z tends to 0, z square into q dash 1 upon z. Okay. If we solve this limit, first of all, limit as z tends to 0, z multiply by p dash. Okay. So if you multiply this by z, so that become 2z square plus 2 divided by z. Okay. This power will reduce to 2. So if you multiply this to z, so we will get 2z square plus 2 divided by z square. Now this limit is, if you put value of z is equal to 0, so 2 into z square, which is 0, so 2 divided by 0, which is again infinity, and this z square multiply by q dash of 1 upon z. So that will become limit as z tends to 0, 2 lambda divided by z square, because this z raised to 4 will reduce to square. Now this is equal to, if you put value of z is equal to 0, so 2 lambda divided by 0, this is again infinity. Okay. So therefore z is equal to 0 or x is equal to infinity is irregular singular point of given differential equation. Okay. Now we are solving last problem of this chapter, which is problem number 15. Okay. So problem number 15 is what? Find out x is equal to infinity is ordinary singular point of Laguerre's differential equation. Also find nature of singularity. So we have to show that that is ordinary singular point. So first of all, Laguerre differential equation is this: x y double dash plus 1 minus x y dash plus lambda y is equal to 0. So this is the given differential equation. We have to convert into this form. That's why coefficient of y dash must be, y double dash must be 1. So we can write given differential equation as y double dash plus 1 minus x upon x, if you divide this by x, into y dash, okay, plus lambda divided by x, if you divide this by x, y is equal to 0. Now compare this differential equation with this. We will get p of x and q of x as p of x as 1 minus x upon x and q of x as lambda upon x. Now again put z is equal to 1 upon x. So we will get P of 1 upon Z and Q of 1 upon Z as, see, in this equation we have to put x is equal to 1 upon Z. So 1 minus 1 upon Z divided by x, which is 1 upon Z, which is equal to. Now this 1 upon Z will go to numerator Z. And if you do multiplication, so this is Z minus 1 divided by Z. So this Z will cancel with this Z and we end up with only Z minus 1. Okay. See, this Z go to numerator, and if you do cross multiplication, so Z minus 1 upon Z. So this Z will cancel with this Z and we end up with Z minus 1. Similarly for Q of 1 upon Z, so if you put value of x as 1 upon Z, so Q is nothing but lambda into Z. Okay. Now we have to find out P dash and Q dash. So using P dash of 1 upon Z as 2Z cube minus Z square P of 1 upon Z divided by Z raised to 4, and Q dash as Q of 1 upon Z divided by Z raised to 4, we get first of all P dash. So P dash is 2Z cube minus Z minus 1 divided by Z raised to 4. So that is equal to 2Z cube, okay, 2Z cube minus Z plus 1 divided by Z raised to 4. Okay. And Q dash 1 upon Z is lambda into Z divided by Z raised to 4, which is lambda upon Z cube. Okay. So lambda upon Z cube. Right. Now at Z is equal to 0, which is x is equal to infinity. So we have to take limit as Z tends to 0 P dash of 1 upon Z and limit as Z tends to 0 Q dash. So first of all, this limit. Okay. Now limit as Z tends to 0 P dash. P dash is what? 2Z cube minus Z plus 1 divided by Z raised to 4. So this limit becomes, if you put value of Z is equal to 0, so 0, 0, so 1 divided by 0, so this is again infinity. And for Q dash, here lambda upon Z cube, if you put value of Z is equal to 0, so this is again becomes infinity. So therefore we can say Z is equal to 0 or x is equal to infinity is singular point. Now we have to find out type of singularity. Okay. So to find out type of singularity, we have to take limit as Z tends to 0 Z into P dash, limit as Z tends to 0 Z square into Q dash. So first of all this factor. So if you multiply this by Z, we end up with 2Z cube minus Z plus 1 divided by Z cube. Now this is equal to, if you put value of Z is equal to 0 in this equation, so 0, 0, so 1 divided by 0, so this is again infinite. Similarly, for Z square into Q dash, so if you multiply this by Z square, so we end up with lambda upon Z. Okay. And if you put value of Z is equal to 0, we end up with Z is equal to infinity. So that's why we can say Z is equal to 0 or x is equal to infinity is irregular singular point of given differential equation. Okay. Now with this we finish all problems of chapter number 4, and our syllabus of whole semester is over now. Okay. Now there are some exercise problems or unsolved problems in your book. So try to solve those problems using the same procedure. If you encounter any problems or a difficulty, I am here to help you. Okay, so you can send me message or anything that you are encountering this type of problem or such type of difficulties, or I will help you out. Okay, or you can call me directly for solving those problems. All the best for your examination.